Good morning, our dear students, and welcome to this morning's class. Today, we want to look at something similar to what we considered yesterday. Today, we already had a class on sampling distribution of the difference between two sample means when sampling is done with replacement. But today we are looking at exactly the same topic, but this time around, sampling is done without replacement. So the only difference between what we are looking at now and what we looked at yesterday is sampling with replacement for that of yesterday and sampling for without replacement for the one we are considering this moment. And we are going to approach this topic this morning by considering two different populations, which we are going to tag population 1 and population 2. So I have population 1, I have population 1, population 1. And let us say that the size of this population 1 is capital N subscript 1. That is the size of this population. Then we equally look at population 2. Look at population 2. This is population 2. And equally, we say that the size of this population 2 is capital N subscript what 2. And let us say that there is a variable of interest that forms this population. And let that variable of interest be represented by what? Capital X. So we are now saying capital X subscript 1 follows a distribution. It follows a distribution with parameters what? Mu what? 1 and then sigma squared what? 1. Close the brackets. The same thing applies with population 2. There is a random variable capital X subscript 2 that follows any given distribution given as what? Mu what? 2 and then sigma squared of what? Of 2. That is to say that this population is represented with a random variable capital X subscript n. And that variable follows a distribution. And this distribution can be any kind of distribution, normal, binomial, Poisson, any kind of distribution. And this distribution, this random variable, having this distribution has mean mu1 and variance sigma squared 1. Of course, this random variable capital X subscript 2 that forms our population 2 follows a distribution with mean mu2 and variance sigma squared what 2. And you do know that our interest is to consider the sampling distribution of the difference. So the key word here is difference between two sample means. Between two what? Sample means. So our interest is on sample means. Our interest is on the difference between these sample means, and our interest equally is when sampling is for without the replacement. So it becomes obvious that we are going to take samples from population 1, take samples from population 2. From the samples taken from population 1, we are going to calculate the sample means. From samples taken from population 2, we are going to calculate what the sample means. And then we obtain the difference between the sample means in population 1 and sample means in population 2. And be able to look at the distribution that these differences now will be able to follow. So we are now going to talk about samples that we are going to take. So we have sample. Let's say that this sample has a fixed size n subscript 1. I equally come here, we talk about a sample. It is going to have a fixed sample of n subscript what 2. So I'm going to take a different sample from population 1, take a different sample from population what 2. And then each time I take that word sample, I am going to calculate what my sample mean. And this time around, you know that we are sampling for without replacement. And the major difference between sampling for with replacement and sampling for without replacement is that in sampling for with replacement, anytime you draw an observation or a unit from the population into the sample, you must have to return that same item or observation before you draw the next unit from that population into the sample. That is when you are sampling for with replacement. But when you are sampling for without replacement, any item that is drawn from that population is not replaced before the next drawer. So that is the difference between sampling for with replacement and for without replacement. And of course, they do affect the distributions of a certain sample statistics. So let us now go about by showcasing this. Let us say that when we come in population 1, that we are going to take this number or this number of what of samples. Sorry for the light has gone off. So we are going to take the following number of what of samples. We have sample 1, we have sample 2, we have sample 3, down to any number of samples that we are considering. And each time I take that sample from this population, the sample size must be what? N1. And from this sample, I am going to estimate my sample mean. Let me say that when I estimate it, I am going to represent it with what? X bar 1. That is the sample mean that I computed from the first sample coming from the population what? 1. The same thing applies here. I am going to take another sample from this population, and that is sample number 2. And from this sample number 2 that has fixed size N1, I am going to calculate what? My sample mean. Let me equally say it is given as X bar what? 1. I will do the same thing here. I will have X bar what? 1. Then I will now continue to do it till any number of the samples that I am considering. The same thing applies here. I will equally take a sample from what? Population 2 that has a size N2. Then from it now, I am going to compute now my sample what? Mean, which I am going to represent with what? X bar what? 2. Equally take a sample again from that population 2. That sample must equally be of a fixed size N2. And from that sample, I am going to obtain my what? My sample mean. Let me equally call it what? X bar what? 2. And then I do it again, X bar what? 3. I continue in that order till I exhaust the number of what? Of samples that we are considering. When I am done with that, our interest is on the difference between two sample means. So we are going to take the difference of these two sample means. So the difference here is talking about we are going to have X bar 1 minus this X bar 2. It is going to give me a value here. Then I do it again with sample number 2, which is X bar what? 1 minus X bar what? 2. It is going to give me a value here as well. I come down to the third sample. X bar what? 1 minus X bar what? 2. It is going to give me a value here. I will continue in that order till I exhaust all the number of samples that we have considered from the two different populations. One thing is important to note here. These sample means that we have obtained here are not going to be constant values because they are random samples that you are taking from a population. So all the units are not the same in sample 1, sample 2, sample 3 down the line. And because all the units are not the same in all of them, the sample means will keep to vary from a sample to a sample. And because they are varying from a sample to sample, they form a random variable. And because they form a random variable, every random variable has a distribution. And as such, Even this sample means which I have here coming from population 1 will have what its own distribution. And when we talk about distribution here, our emphasis is going to be on the mean of this distribution, on the mean, on the variance of this distribution, and equally perhaps on the shape of this distribution. The same thing applies here. Their values are not going to be constant. They keep to change from sample to sample because the units are not exactly the same in each of the sample. And because they vary, they form a random variable. And then because they form a random variable, there must be a distribution of this random variable in terms of the mean and then in terms of the variance and perhaps in terms of of the shape. The same thing applies with this difference. Because the value here and the value here are not going to be the same thing. They vary. So if you take their difference, you have a value here. This value and this value aren't the same thing as well. So if you take their difference, they equally vary. So these values I'm going to have here now equally begin to change from sample to sample. And because they change, they form a variable, a random variable, which as well have what? A distribution. So there are three random variables here. The one formed by the means coming from population 1, the one formed from the means coming from the population 2, and then the one formed by the difference of the means coming from the samples taken from the two populations. Now, look at where our sampling for without replacement comes in. We are told that each time we are sampling for with replacement, and then we take different samples from a population of size what? N. Okay? And then we are now to look at the distribution of these sample means. It has been established that the distribution of this sample means will be that our x bar 1 will follow a distribution. It will follow a distribution that will have the following parameters. It will have what? Mu 1, comma. It will have what? Sigma squared what? 1 all over what? N1. Into, we have what we say capital what? N1 minus what? N1 all over what? Capital what? 1, N1 minus what? 1. Close the bracket. Then we now close it with this kind of a bracket. I repeat. Whenever we have a population of size N1, and that population is represented with what? A random variable, capital X substitute 1, that follows a distribution with mean mu1 and variance sigma squared what? 1. And then we take different samples from this population. And each time we take a sample, and that sample we are taking is for without replacement. And then we take different number of what samples, and from these samples now we estimate what they mean. We are told that the distribution of this mean will be given this way. That the means taken from this population 1 is going to follow a distribution that has the mean mu1 the same as the population, but the variance is going to change. The variance here is sigma squared 1. The variance here is sigma squared 1 all over n1 into what? N1 minus capital N1 minus small letter n1 all over capital N1 minus 1. And this quantity here, which we call capital N subscript 1 minus small n subscript 1 all over capital N subscript 1 minus 1, is what we call the finite population correction factor. It is only necessary when we are sampling from a finite population or when we sample for without replacement. So in sampling distribution, when one says finite population and one says sampling for without replacement, they are equally saying the same thing. The same thing applies when we come to population 2. So population 2 is now going to be that my x bar 2 now here, my x bar was 2, is going to follow a distribution. And then this distribution is going to have mean mu what 2, comma, we have sigma squared what 2 all over what n what 2 into capital N subscript 2 minus small letter n subscript 2 all over capital N subscript 2 minus 1. We close the bracket and then we close it this way. And of course, this quantity as well we have here is what we call the finite population correction factor. Now we have been able to show the distribution of the means coming from what population 1, the distribution of the means coming from what population 2. So by implication, when we are told that this mean is 5 and we are told that this variance is something like 1.2, and we are told to find the distribution of the means that is drawn from that particular population, we are going to come here. If here is 5, here will equally become 5. But if here is 1.2, for instance, it is not going to be 1.2 here. It becomes here 1.2 all over n1, where n1 is talking about the sample size. So if this sample size is 20 or 15, it is going to be 1.5 all over what? 15, open a bracket. They must have given us the size of this population 1, we put it here, minus that 15 all over that size minus 1. We must have to use that quantity to multiply this variance before we can then get the variance of the distribution of this x bar 1. The same thing applies with that of the second population 2. And we are going to determine the distribution of this difference, which is exactly what we are looking at today, making use of the properties of the distribution of x bar 1 and then x bar 2. So you are going to permit me to clean the top while we determine the distribution of this difference, making use of these distributions here. And do remember that this mu1 is what we call the mean of this distribution. And there are different ways that it can be written. You can see some people write it this way. They will come and they will call it what? E of x bar 1. E of x bar 1 means what? Expected value of x bar 1. And of course you know that expected value is talking about the mean of a random variable. Then they will now say that it is the same thing as mu of what? X bar what? 1. You can still see them write something like this, mu of x bar 1. Then the answer of this is what we call our mu1, which is what is here. When they talk about this variance, they can write it like this. They say var of x bar 1. It is the same thing like writing sigma squared of x bar 1. So the same thing as the quantity we have here, which is sigma was squared 1 all over n1, then into what? Capital N1 minus n1 all over capital N1 minus 1, close the brackets. The same thing applies in population 2. So anytime you see expected value here, it is still talking about what? Mean. You see it written this way, it is still talking about this mean that is here, then which is written like this. The same thing applies here. So you are going to permit me to clean the top. Let us now determine the mean of this difference. Okay. When we want to talk about the mean of what of the difference, we are now talking about what the x bar 1 minus x bar 2, the distribution it is going to follow. And of course, we are now going to talk about the mean. If you talk about the mean, you are going to have expected value of x bar 1 minus what? X bar what? 2. Just like you did expected value of x bar 1 and you did expected value of x bar 2 to get your mu1 and mu2. We are now going to use expected value of x bar 1 minus that of x bar 2. So this is going to be, using this expected value to open this bracket, we have E of x bar 1 minus what? E of what? X bar 1. And this thing becomes, remember that expected value of x bar 1 is mu1, so now it becomes what? Mu1 minus. Expected value of x, here is x bar 2. Expected value of x bar 2 is given as mu2. so minus what? Mu2. Which means the mean of the sampling distribution of the difference between the two sample means is given as the difference between the two population what means. So assuming that this population mean here is 7 and this population mean here is something like what? 10. And we are now told to find the mean of the distribution of the difference between the two sample means. We simply come here and say whatever value that is here minus whatever value that is here is going to give us here. When we talk about variance, look at how the variance is done. So the variance is going to be var of what? X what bar what 1 minus what? X bar what 2. Look at how it is expressed. It will be given as var of what? X bar what? 1 plus var of what? X bar what? 2. This is how to show this kind of a thing. That is how to show this kind of a thing. The difference is that when we are talking about expected value, this retains its negative sign. But when we are talking about variance, this thing becomes what? A positive sign. Okay? And then it is very simple now for us now to determine this. Here is var of x bar 1. We come here, we ask ourselves, where is our var of x bar 1? var of x bar 1 is given as this quantity. So I will now say that this is now going to be, this will now be given as, we have sigma squared what? 1 all over n1, then into, we have capital what? n1 minus n1 all over what? Capital N1 minus what? 1. We close the bracket, we say plus. Here is var of x bar 2. And we know that var of x bar 2 is given as this quantity that is here. So I will call it up and put it here. So it becomes what? We have what? Sigma squared what? 2 all over n what? 2 into capital N2 minus n what? 2 all over capital N what? 2 minus 1. We close the bracket. So this thing becomes the variance of the sampling distribution of the difference between the two sample means. So fully, the distribution will be written this way. Fully, the distribution will be written this way. Look at the way that this distribution was written here for this one. Look at the way that this one will be written. So this one will be written as that the distribution now, so distribution of this one, that our x bar 1 minus what? X bar what? 2 will now follow a distribution. You follow a distribution which mean mu1 minus what? Mu what? 2 and variance sigma squared 1 all over n1 into capital N1 minus n1 all over capital N1 minus 1, close the brackets, then plus. We have sigma squared what? 2 all over n2 into capital N2 minus n what? 2 all over what? Capital N2 minus 1. Close the bracket and then close this bracket this way. So that becomes the distribution of the sampling distribution of the difference between two sample means where sampling is for without replacement. That is the reason why you are seeing this quantity finite population correction factor for that of population 1, finite population correction factor for that of the population 2. However, there is something they usually say. They say the sampling distribution, or they say the standard error of the sample means. When they talk about the standard error of the sample means, it is just the square root of the variance of the sample means. So when they say something like that, we present it this way. See what we are now going to present. We are now going to present it this way. Sampling distribution, standard error of the sample mean, standard, permit me to write it std.e of the sample mean, standard error of the sample mean. This is square root of var of x bar 1 minus what? var of x bar 2. And we have gotten everything under here to be this quantity. So I'll just use a square root this way and then put the entire of this thing, sigma squared 1 all over n1 into what? Capital N1 minus N1 all over capital N what? 1 minus 1, close the bracket, plus. We have sigma squared what? 2 all over N what? 2 into capital N what? 2 minus N what? 2 all over capital N2 minus 1, close the bracket. And the good news there is that if you are to be asked questions in all these things, you must have been given the value of what your N1 is, what your N2 is, that is size of population 1, size of population 2, size of samples coming from population 1, size of samples coming from population 2, and you must have been told somehow the variance of population 1 and then the variance of population 2. So it is just by substitution that you are going to arrive at everything that is needed here. So that is what we call the sampling distribution of the sample mean. However, let us mention something before we take some examples to illustrate on the board. Now, at times we have what we call approximated value of the finite population correction factor. And you might be going through the pages of textbook and you run into that, and then you begin to have problems now reconciling it with what we have here on the board. At times, you see them write something like this as finite population correction factor. Hmm? At times, you see them write something like this. They will say it is given as 1 minus what? N1 all over capital what? N what? 1. They will now call for that of population 2. 1 minus what? Small letter N2 all over what? Capital what? N2. You might see them use this and use this to replace this quantity and replace this quantity. But I'm going to explain. The right one to use is this one we have shown you earlier. But let me now tell you the condition at times when people begin to consider this one. And for you to consider this one, you must have been given the hint in the question that you should consider it. Otherwise, when nothing is said about it now, you stick to the one that is unapproximated. This one is the real finite population correction factor. This one is approximated finite population correction factor. What they mean by this is this. If you come to this, what I have here is capital N1 minus N1, small n1, all over capital N1 minus 1. When this N1 is large, reasonably large, subtracting 1 from it doesn't really make a difference. You can imagine something, a value for something like 1 million, and then you subtract 1 naira or you subtract 1 from 1 million. You can imagine that it's not going to have a significant impact on that money. So at some point in time when this N is reasonably large, they begin to look at N and N minus 1 as being the same. And if you are looking at N and N minus 1 being the same, it implies that when you have something like capital N1 minus small letter N1 all over capital what? N1 minus what? 1. And you are saying that this your N1 is large enough. Subtracting 1 from it doesn't make sense. Because if you use the one you have subtracted 1 to divide this numerator, the value you are going to get and the value you are going to get when you did not subtract 1 and you divide, they are going to be almost the same thing. Okay? So in that case, we can easily let go of 1. And then what we are now going to have becomes capital N1 minus this N1 all over what? Capital N1. And if you have something like this now, you can easily turn it to something like this. Turn it to something like this means that this is going to be, this equals capital N1 all over this capital N1 here minus what is here is what? N1 all over what? Capital N1. This quantity and this quantity are the same thing because if I take LCM here, I return back here. So this and this will cancel to give you 1. And that's why I'm having 1 minus N1 all over capital N1. The same thing applies when we are talking about population 2. It is called approximated value, and you can only use it when you are told to do so. So permit me to clean the board. Let us take one example to illustrate what we have discussed thus far. We have a question here, and that question says, the question says, the question gave us value of the size of the population, and equally gave us, they call it what? They have quantity. They have quantity. Call it quantity. Quantity. And then they call it factory one. Call it factory one. Factory one. And then they have factory two. They have factory two. Factory two. And then under this quantity, they have capital what? N. Then they have what is mu. They have mu. They have sigma squared. And then they have what? N. Under this factory one, they have 500. Then here they have 60. Here they have what? 100. And then here they have 50. Under factory 2, they have 400. Then they have 55. They have 64. And then they have what? 41. And the question here is that we should obtain the mean of the sampling distribution. So we should obtain what? E of x bar 1 minus x bar 2. That's what they mean by obtain the mean of the sampling distribution of the difference between the two sample means. Then they have this one again to be this way. They say we should equally obtain var of x bar 1 minus x bar 2. And then we should obtain the STD dot E, sampling distribution of the sampling standard error of the sample mean. And one important thing here is sampling is done for without replacement. That is additional information here. Hint, sampling is for with replacement. Or hint, sampling from a finite population. Without wasting time, we now come here and have solution. We have solution. Have solution. Then we begin with the first one, which is I. We call it E of x bar 1. E of x bar 1 minus x bar what? 2. You remember that this was expressed as what? E of x bar 1 minus E of x bar what? 2. This is equals. And do remember that we say that E of x bar 1 means expected value. Okay? Talking about expected value of that random variable. And remember that we earlier had shown that expected value of the x bar 1 is given as mu1, and expected value of x bar 2 is given as what? Mu2. The same thing like that of the population. We have shown earlier that this is given as what? Mu1 minus what? Mu2. So this implies we return back here and look for our mu1 and look for our mu2. What this means here is this is n. So under this factory 1, we are talking about n1 being 500, n2 being 400, mu1 being 60, mu2 being 55, sigma squared 1 being 100, sigma squared 2 being 64, n1 being 50, n2 being 41. That is how to interpret this. So I will now quickly say, what is my mu1? My mu1 is 60. So here becomes 60 minus. What is my mu2? 55. So this is 55. And then the answer becomes 5. And with this, you have been able to see the mean of the sampling distribution of the difference between the two sample means. Then when we now come for that of what? Of the variance here, we earlier had shown that the variance is given as I. We showed that the var of x bar 1 minus x bar 2 is given as general square root of, we have sigma squared 1, or no, not square root. It's only when we talk about standard error we put square root, all over n1 into what? Capital N1 minus N1 all over what? Capital N1 minus 1, close the bracket, plus. You have sigma squared what? 2 all over what? N2. You have capital N what? 2 minus what? N what? 2 all over. We have capital N 2 minus what? Minus 1, close the bracket. So we now evaluate this. This becomes, we go and look for the variance of what? Of population 1. Variance of population 1 is 100. So we have 100 all over. Talk about the sample size from population 1, which is this, in population 1, which is the 50. Have all over 50, we open a bracket. Here is capital N1, which is 500. So we have 500 minus. Sample size is what? 50. So we have minus 50 all over. We have what? 500 minus 1. Close the bracket, plus. Here is our sigma squared 2. My sigma squared 2 is 64. So we now have 64 all over. The sample size is 41. 41, open a bracket. Population is 400. So we have what? 400 minus. Sample size is 41 all over. We have 400 minus 1. Close the bracket. So anybody can evaluate this. This minus this will give you 450 all over 499. Then this one now will give you, if you remove this in here, you have about 339. Then all over this, which is the 399. So anybody using a calculator can easily evaluate this value with ease. So and then when they talk about now the standard error, so you now say this is I, the standard error of the mean. The standard error of the mean, STD dot what? E of the mean is the square root of whatever value you have here, 100 all over 50, then into 500 minus 50 all over what? 500 minus 1, then plus. We have 60 what? 4 all over what? 40 what? 1 into 400 minus 40 what? 1 all over, we have 400 minus 1. Get the square root of whatever thing that you have here. And I want to make something clear here once again. At times you see people say that a finite population correction factor is given as this. That the finite population correction factor is given as a capital N minus N all over what? Capital what? N minus 1. Here I'm not paying attention whether it is for population 1 or population 2. At times you see other people talk about that the finite population correction factor is square root of capital N minus N all over capital N minus 1. Both of them are correct depending on the question asked to you. If you are dealing with variance, which is the one that you have here that is not under square root, this is the finite population correction factor. But if you are dealing with the standard deviation, of course, it becomes the square root. So if you see them talk about this and talk about this, they are correct, but you need to pay attention to understand the context under which they are now making that they are differentiating them. Okay? There are still more questions that we are going to solve under this particular topic that we have started handling on sampling distribution. But to manage the size of our classes, we are going to stop the class today. In the next class we are going to have, we continue to look at other questions that one can be meeting in this kind of question. Thank you very much for your presence in our class today. Thank you very much for your audience. Do not forget to subscribe to our YouTube channels and then follow our classes. Stay connected till our next class.